The first talk is by Andreas Schenk, and he will mainly concentrate on visualization of 3D maps.
Okay, as Tom said, we'll concentrate on visualization. So, how you get your nice images once you really have assembled your data set in Merge. We'll try to be a little bit faster that we can go along. Okay, so that's all we also already showed about the processing of images, processing of diffraction. And I thought you focus here on the very last part. Really, once you have discretized data set and for diffraction, once you have done molecular replacement and refinement, how you can visualize this. So, what do you need to be able to visualize your data? You need discretized data set. So you need to have the data set after last line phase. And you need amplitudes and phases. This means it's quite easy if you have images, because there you get both. You can do combination of diffraction data, take amplitudes from there, use use the phases from the images, completely kick out the amplitudes from the images, and do just a one-to-one combination. But there are also probably some more clever ways to do that, and Brian will talk more about that. But you can do there, you don't really need two full data sets to get an indent 3D map. And the third method is just to record pure diffraction, and then you have to do some kind of molecular replacement and refinement to get amplitudes. And once you have these, you normally have this data set, and you save it as a binary empty set file. That's the standard file format used for CCP4, the one we also use in the faculty. So in 2DX you can convert to that, you use the CCP4 directly, and then you just do a easy back transformation using the standard FFT. So this means from your data in Fourier space, where you have these lines, your back transformation, you get your 3D map, where every voxel just represents your density in that part of the 3D space. And here, that's also the point where the non-crystallographic symmetries kicks in. You often have, in your map, you have additional symmetries which were just not covered by the crystallographic symmetry. There we have mainly two different possibilities to handle these. So non-crystallographic symmetry is just symmetry which is not caused by one of the symmetry operations of your given space group. And either you can use this just to average your protein even more in real space, or the second way you can go is you can just run a free shell correlation or free ring correlation if you have a 2D data set to assess the quality of your data. So you can use it as an additional measurement how well your two copies of your protein, which are symmetry related, match to each other. And for diffraction data, you can also put in this information about the non-crystallographic symmetry into molecular replacement and refinement, get there better refinement. So that's just one small example of the non-crystallographic symmetry. That's a project I was working on recently. Projection map. As you can see here, you have here that's diameter of your structure of your protein. Here, the red dots, these are the crystallographic P2 axis. But because this dimer has different inter-dimer crystallographic contacts, it makes a somewhat funny arrangement, and you see you have here suddenly an additional P2 axis of the dimer itself, which is not a crystallographic one. Huh?
Isn't this P2 to sub 1 2?
It is already P2 sub 1 2, but this one here is still in addition. You can see it here. This here is not here on the axis. Slightly more down, and this here is slightly more up.
Okay.
And that's just because here you have the green. Here the green density is always the same one. And here they are really opposite each other. And here they are shifted somewhat, so you have two different contacts. Because otherwise your unit cell would just be the right part here, and then this would be so rectangle. Like this, it's not. That's just a small example. This can happen quite often. We also see it often in the aquaporin crystals, if you have double layers. Sometimes you have more than one tetramer in the unit cell. You can then just average them in real space. Okay. Now, once you have this map, what do you do with it? There are different ways to visualize your map. So the easiest two possibilities are just take slices out of it, visualize, have a look at the slices, or do projections. But in the end, I mean, you determine the 3D structure, so you also want to visualize in 3D. So normally you go for the isocontouring and then do ray tracing, you get an even nicer image. This you can nicely put into your paper. So just to have a look at slices, that's a very fast way to look at the 3D volume. It just has one problem. Normally your density maps have a better resolution in X and Y because you have a missing cone in a certain direction. So if you just look at XY slices, they normally look quite nice, and you don't see that actually the resolution in certain dimensions is not that good. This you don't see here. What?
That's good.
Yeah, depends. You always take only what you see. That's the problem, is it? As soon as you can do a real 3D visualization, there you see it. So, yeah. The second way is just do projections. You basically do projection at an arbitrary tilt angle. Either you can do it in Fourier, using Fourier summation, as we do in night theory. You can do it as an interpolation in Fourier space, as is done in the electron, what you showed in the other lecture. But that's normally not used to look at your data. It's more used than to go back and refine the data. Because it's not that much fun just to watch these. It's just a small example, an aquaporin at different field angles, projection. Okay, so now we are coming to the more interesting stuff. Isocontouring. That's basically the same principle as you see on the walking maps. So basically you have a profile, and just at certain heights, you draw the lines. So you see here these nice lines, and you can do exactly the same thing if you have a projection of an image. You have a grayscale image, and just at certain grayscale values, you draw a line. That's quite easy. Then you can extend the whole thing also to 3D. The only difference is, instead of getting a line at a certain density, you get a surface. Basically from here, from the voxel, you get to a surface. With this, you can quite nicely visualize in 3D your protein. That's an example done in Pheno. There are also a lot of old programs like Timel or Chimera can do the same. As you can see here, in green you have one density, and in yellow there's a different threshold. So using sometimes meshes and the full surface, you can do more than one threshold, and not that use too much, because otherwise it gets too complicated. Okay. Then there is even a nice way to do that. Once you have your surface, you can apply it to a ray tracer. A ray tracer basically simulates the way the individual rays of light travel. So it goes back from starts from the camera, goes back and see what objects are hit, which light sources are hit. So here you get a ray which hits the first object and it travels to light. So this one here will be more light, and the other one here first hits the bottom surface and then doesn't hit any light source, so here you have a shadow. Like this, you can really add mirror effects and shadows to your image. And this just helps the eye to get a better representation of the three-dimensionality of your object. So in a way, you just get a better depth, you get a better understanding what's happening in a certain dimension you can really see. I mean, for example, here you have the shadow, so you immediately know that these small spheres are at the front of the image, not at the back. It's, in a way, it's not it displays what happens in reality, because normally proteins are not exposed to light source, but it just helps you to visualize the three-dimensionality of the protein. Okay. There's one way also, in a way, the best way to look at it is you really can have a 3D image. But there you need to use some tricks, because normally your screen is always a 2D object. So you need to trick your eyes that you really see something in 3D. And the basic way to do that is just you have to provide two images, and to have to make sure that just one eye sees one of the images and the other eye sees the second one. With this, then the brain assembles back and sees a 3D image. One way to do is just to draw the two images beside each other. Then you have to focus your eyes, is that basically the 2 points overlap, and then you will see it in 3D. But there are also some other ways, some technical ways which can help you to do that. A quite recent development were these stereoscopic displays. You can now buy them. I think they cost around $3,000 to $5,000 or so. Which basically have a TFT, a non-TFT display. And what they do is, it just every odd pixel, they display the image for the left eye or for the right eye, and every even pixel they display the image for the left eye. And then in front of that, they have some kind of barrier that really just the left eye just sees these and doesn't see these, and vice versa. You can do the same also with the TFT display, which has small lenticular lenses in front of every pixel pair. If you ever had the chance to look at these images, these displays, they look quite nice. The only problem with it is, because you display both the image for the left eye and for the right eye simultaneously, you just get half of the resolution of the original display. That's in the moment the biggest limit of these kind of displays. But I mean, probably the sizes of TFTs will develop and the cost will go down. So in the future, this is for sure a direction to go to really have just one of these displays and to watch it in 3D.
How prone are these displays in regard to viewing distance or viewing angle?
And normally you have an optimal viewing distance. I mean, the one I saw, you can move your head a little bit and you still get 3D image, but you cannot move it too much.
In Germany, you would also say it depends on if you are from the south or the north, because in the south the eyes are more narrow.
So, depends on personal. But there are some of these displays which were manufactured in a way that not just have one single optimal position, but you have kind of 5 cones where it's good. But always in between you then have some positions where you don't see the image in 3D. So that's also one of the problems with these displays. You shouldn't move your head too much if you want to work with things. It can be a little bit of a problem. Yeah. Second solution is nowadays used quite often because it's older. That just used this kind of shutter glasses. There you use a normal CRT monitor, and you just have a set of glasses. The monitor just displays first the image from the left eye, then it displays the image from the right eye, then again it displays the image from the left eye. It does that very fast, preferably at something like 120 Hertz. You have a flicker-free image. And then just basically the shutter glasses are synchronized to the monitor, so that if the left image is displayed, your right eye is basically covered, and you just see by this left image, this left eye. These work very well, but as with all 3D technologies, after a while you still can get a headache if you look too long into the monitor listings. But they work quite well, and also here you really can move your head, and you also can change the distance. It's not that sensitive to the position of your eyes. But the drawback is you normally cannot use these TFTs. I think by now the TFTs are slowly faster, or I think the newest ones are fast enough that you can do it. But just the older TFTs were not fast enough to display one on 20 images a second.
We actually had a TFT screen demoed about 3 months ago that works with this setup.
Okay.
So they're starting
Cool.
to come onto the market.
Yeah.
And it worked, yeah, I mean, it's comparable to CRT.
Yeah. Okay, that's cool. Because that's also basically for until recently, this was the main drawback that you really need one
Yeah.
big old security monitor to do that. Okay. And there's one last possibility what you can do. And it's just instead of looking at static pictures, you assemble them into an image. So you basically just you do different images from different sides of your protein. You can do this with the same tools, Dino and Puffray, or whatever you want, and just set them to this. Then you have a stack of images. Then you can use a tool like MPEG Encode, or for sure also some tools on Windows, but I don't know the names. And you can just assemble them into one continuous movie. And that's basically what you get. This also helps you to really get a feeling of how your protein looks in 3 dimensions, even though you still have a 2-dimensional screen. Stop. Okay, so that's basically the last slide. Just want to give you an overview and also the links where you can find these different tools. As I said, this before that you can use it for back transformation. And the whole bunch here basically used for the ISO contouring. But also, I know from Dino you can export it that you then afterwards can use in Puffray to do ray tracing. I'm not sure if could be that you can also do this the other 3, I'm not sure. Because I mainly use Dino because Oscar wrote it, and so if I have a question, I can just turn and ask him.
And also, I hit you if you use something else.
Yeah, that's also true. He doesn't like it if you use something else now. So we just use it if he's not there, basically. Okay, so basically this was everything. Thank you very much for your attention, and quickly for the acknowledgement. It's here the same guys for image processing, and I just want to thank them for to give thanks to Fabio, Mohamed, and Dini, because this was basically a project here where we have this nice little crystal. This is funny NCS symmetry and this funny 2 crystal contacts. Okay, so thank you very much for your attention.